You should have the homework for chapter 1, section 1. Pass it in towards the center. I'll come around the aisle and pick it up for you all. Logically equivalent propositions generate for me the same truth table for all possible cases of substituting in the values. We did this Monday. How? Or did we do this Friday? We did this in the past 2 days. Aha. We actually went through and looked at P implies Q and not Q implies not P. And those turned out to be logically equivalent. Because no matter what combinations of trues and falses you put in for the P's and the Q's, you got the same result out. Okay. There's another way to do this that only requires you to look at one truth table, but it's a truth table that's more complicated, unfortunately. So I prefer to say this idea is the way I want to think of it, but the textbook wants me to take it a step further. I want to look at this. All I did was I took the two things that I think should be equivalent and I made them into a biconditional, as an only if statement. Okay. What we said earlier was that the true or false of this should match the true or false of this. When is the biconditional true? When is the biconditional false?
So it's true on both sides. So both the true and false and false.
Which means if these two really matched, this statement would be true all the time, wouldn't it? A compound proposition. A proposition that is always true, regardless of the values of P and Q and R and all the variables, is called a tautology. This is the opposite of our contradiction idea. That I remember we talked that one about on Monday, because we're talking about it in terms of system specifications. So I will define two sentences to be logically equivalent if the if and only if is a tautology. Now, I used P1 and P2 instead of using P and Q because we think of the lowercase letters as individual variables. I want to think of P1 as some compound proposition and P2 as some other compound proposition. Always true is a tautology. Always false is a contradiction. That leaves out a lot of options, doesn't it? Like our system specification option, right? I just needed it to be all true once. That's a conditional statement. Well, that makes sense. We called them if-thens. We would have a conditional idea or a contingency. It depends on which values are true and which values are false. This comparison between these two statements was first formalized by a guy by the name of Augustus de Morgan, and this is one of de Morgan's laws or de Morgan's rules. There's another one, we'll get to in a minute, two most common versions of this. But this is basically a distributive property. I've got the not in front of the parentheses. So not P or Q. I claim means the same thing as not P and not Q. Let me pull back up an example from previously. We had it snowed, it is below freezing. Either it snowed or it is below freezing. Negate that sentence. I need the truth values to flip completely, right? So I need it to not be snowing. I need it to not be below freezing. I need both of them. So instead of an or, I should have an and. I think. How do you know whether or not I'm blowing smoke out my ass?
Because there's not fumes coming out of.
Yeah, there's no fumes coming on my hands. I like that part. Let's do a truth table. Now, we have our choice because I said we could really just look at one sentence. So I'm going to take this idea and turn these two sides into a single proposition. And the proposition is going to be an if and only if. So I want to make one truth table for this big ugly mother. Fortunately, I can build this truth table using all the stuff we did in the homework you just gave me. All I have to do is make the right number of rows, build it one operation at a time. And then again, you have your choice in how you want to lay this out. Do you want to do the left side first? Do you want to do the right side first? What order do you want to do the columns in? We have all sorts of options here. But I know that if I want to try and be standard here, I should start with my 4 options for the truth values. Order dependent, everything from here out follows just from those. Are we going to do the left side first or the right side first? Left. So if I'm going to do the left side, I got to work from the inside out. My order of operations says I do the parentheticals first. So the first thing I'm going to do to build the left-hand side is I'm going to do the or statement. When is or true? When is or false? Emily.
The or is inclusive, so anytime one of them is true, it's going to be true.
In another textbook, unfortunately not in this one, all 5 of my base operations had one sentence remembers. One sentence mnemonics. And is true when both are true. Or is false when both are false. If then is only false, TRO. When the antecedent is true and the consequent is false. If and only if is true, when they agree. All my binary operations can be reduced to one sentence each. I like that because it means I don't have to memorize truth tables, just to remember a couple sentences. Okay, to make the left-hand side, I need to negate this. There we go. Now, since that's the left-hand side, up here I'm going to write LHS, left-hand side. Try to remember that. In order to do the if and only if, I have to do the right-hand side. So I got to work from the inside out. Stop me in the middle is not a bad idea, no matter what, Isaac. I'm more than happy to say, whoop, let me back up. Somebody still got a question. Okay. Right-hand side, inside out, order of operations says not comes before and. I need not P, I need not Q. Not flips the bit. Again, one sentence. Again, I'm doing and. And is true when? Both are true. Only time that happens is down here on the bottom. Everything else has at least one false in it. Now, to my mind, this is a perfectly good place to stop. But I'm going to be a pedantic bastard like the book wants me to be. I haven't done the if and only if part. So the last column would be left-hand side, if and only if, right-hand side. And the reason I abbreviated that is otherwise I'd run off the edge of the page because I'd run out of room. But really now I'm comparing these two columns. And an if and only if is true when they agree. Agree, 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 agree. I have a tautology. And if I have a tautology at the end of this if and only if table, then my two statements are logically equivalent. Whew. You could have stopped here and indicated, hey, look, this column and this column are identical. And since they generate the same results for all possible true and false combinations, they must be equivalent. So I am of the opinion personally that this column is kind of unnecessary, but it is pretty to see all the truths there, right? Yay. Questions? Two variables, 4 rows, 3 variables, 8 rows, 4 variables. I'm counting the powers too, aren't I? Every time I add another variable, I have to reproduce the entire chart with that new variable, either all true or all false. So if I have n variables, I'm going to need 2 to the n lines. I mean, 5 variables and I'm at 32. Normally on a standard sheet of paper, there are 66 lines of text. So I get to 6 variables and I fill the page with one truth table. That hurts. I don't want to do that. So a legitimate question. I have P and Q or R. Do I need the parentheses? Why? That was what we said should make a difference. Does it make a difference? Let's find out. Are these two equivalent? The only way I'm going to find out is to make a freaking truth table. Now, that's not 100% true. There is another way for me to find out. The other way for me to find out is to physically build 2 circuits with the ands and the ors in the proper order. You have your soldering iron and your chipset in front of you. Yeah, me neither. I'm not going to do it that way. The most amusing thing I saw over the Christmas break was I saw Baby's first propositional logic book. I wish I was making this up. It has 2 buttons. And every time you open a page, it tells you push not, and it turns the light on and off. You push or, you go through the entire thing. Teach your child logic from the ground up. Okay, so how many rows do I need in this truth table? I'm sorry, I heard somebody. 8. And again, my default is that the one on the right flips back and forth every one, and I double it as I move leftward. Okay. Need to tuck this in so I can actually see that at the top of the page. I want to do the left side or the right side to do the if and only if, or I could do them as separate pieces and then just compare the columns. It's 2 to the power of how many variables we have. 2 times 2 times 2 is 8. In order for me to build these, I can only do one operation at a time. And is true when both are true. It's false every other time. Now, notice that I was only paying attention to P and Q, not R for that part. And that's why I only got trues in the top row, top 2 rows. Now I'm going to pay attention to this and R, and I can ignore P and Q. And that's my left-hand side. Okay, that's an or. All I need is for one of them to be true. Yes, 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 no. Yes, no. Oop, I wrote no. Should have wrote false. Yes, no, yes, no. That's my first proposition that I got all the way finished. That's the left-hand side, yes? A couple of you are still looking at this going, wait a minute, talk to me. Isaac, question? Yes.
What is the rule for the stuff which is true?
So if I'm doing an or is true when one or more is true. It's only false when both are false. So the only time I'm going to get an F is when I have 2 Fs. Here in the 4th row, here in the 6th row, and here in the 8th row. At least one. That's an inclusive or. Now, since I didn't actually write the if and only if, I'm just going to put a star on this column. That way I remember this is one of the things I wanted to look at. Now we'll build the other one, which means I start over here with Q or R. I got to jump over some stuff, right? I need to ignore these, and I need to ignore P. So I'm going to build the Q or R. And Isaac, we're going to use exactly the same rule here. At least one true is enough. So I'm good, 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 no. Good, true, I'm good, nope. And now, finish that out, P and Q or R. And is true when both are true. So I need the first column and the most recent column. Good, that's both true, both true, both true. Oh, only one is true, false. Only one is true, false. Stop right there. Why? Please? Bingo. That column's got a star on it. And in the 5th row, I have a difference. Now, I actually think I may have more differences. False and true gives me a false, so that one's the same. False and true gives me a false, that one's also different. False and false give me a false. So there's more than one difference between the 2 starred columns. And if they're different anywhere, these are not logically equivalent. So I can answer the question, no, and this is my justification. I don't care whether you finish that last column or not. You'll notice what I didn't do was I didn't make the if and only if column. But if I had made the if and only if column, it would be true, 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 false. Because they only, if and only if is only true when they agree. So that's the fifth row is going to give me that first place where I lose my ability to be a tautology. Questions? There are a lot of propositional equivalences. Lots of them. And I don't want to spend my time memorizing them. So those of you with physical textbooks, page 29 has 3 tables we're going to use. Put a post-it note somewhere on this page. If you've got a PDF version or an e-version of the book, put a postmark or a flag or something in that part of your PDF. Let's play with these. 29. They are. There are 3 different tables here. Table 6, 7, and 8. These first sets in this one have names. And I'll be 100% honest with you, I don't remember the names all that well. And I'm perfectly okay if you don't remember the names either. But I also know that excessive memorization just to barf this up later is a useless skill. So when the exam rolls around, you get to make a formula sheet for this. That was the hint dropping. In this table, a capital T means a proposition that is always true. A capital F means a proposition that is always false. When you and with a true, then it only depends on the other piece. Because and is true when both are true. If the right side is always true, then the left side is the only piece that's going to matter. You can simplify by removing that extra true. Similarly, if you or with a false, well, in order for an or to be true, one of the pieces has to be true. If this one is always false, I can ignore it and just look at what's going on in this one. The reverse generates trues and falses. P or true, or only needs one true, you gave it to me. P and false. False is broken if either of them is false. You gave me one that's false. That'll be broken. And then we keep going. You know, if you or something with itself, then it just has to be true once. If you and something with itself, it's the same as itself. Double negatives. It works in English, it works in logic. Commutative rules. Whether you and or, you can switch the order. Not true with the if and then. We saw that with our converse and our inverse behaviors. Associative rules. This kind of looks like what we just did. What we just did wasn't an identity. So why is this one working?
They're all or all and.
They're the same. The one we just did was P and Q or R. When they're all the same, I can do them in any order I want. Distributive rules work. You have an or outside an and, you can distribute the P or to each of the two pieces, and the and stays in the middle. The and in the middle here is in the middle here. Similarly, if the or is in the middle and there's an and on the outside, I can distribute the same way. Here's my buddy De Morgan. When you distribute a not, you have to flip the truth bits on the inside. You have to flip ands to ors, and vice versa. So if you have an or on the inside and you have the negative outside the parentheses, you end up with an and on the inside. So De Morgan reverses all the truths and the operation. We're actually going to see this again in a different context. And those of you that have done anything with sets or classes, programming classes, may have seen this in that context as well. It's the same De Morgan, it's the same rule. If something appears twice, we can kind of suck it up and only need it once. So we can absorb an extra or P on the outside or an extra and P on the outside when there's an or on the inside. If Shakespeare was a logic person, Hamlet would have been really short. To be or not to be? True, I'm done. Play's over. Or only needs one of them to be true. P is true, then not P is false. But if P is false, then not P is true. One of them has to be true. And needs both of them. These are going to have opposite values. You can't get both of them to be the same. This could be a shortcut to me doing logical equivalencies without doing a truth table. Because I could try and work my way from one side to the other without ever actually building the truth table. You'll notice that a couple of my operations are missing. What's missing from this table? Yes, the exclusive or can be contained within an or and a not. Turns out we can make it from something else. I would like to show that. It's not up here. Now, if you do it in words, I think this is really easy. Our exclusive or means either P is true or Q is true, but not both, right? What do I say over here on the right? P or Q and not P and Q. P or, but not both. Now, this one isn't in, I think, so I would have to make a truth table for this, right? I'll leave this as an exercise for you. It's only 4 rows, the shorter one. Promise I believe the things. But there are 2 other operations that we're missing. What other operations were missing from that giant table? Conditionals and biconditionals. That's what tables 7 and 8 are. I really like this first one. P, if P then Q, is equivalent to not P or Q. That one is going to be useful to us, as well as this 5th one. The opposite of if P then Q is P and not Q. Put a little star by this one. This one's going to come back to us again. That one is kind of important. Rarely do I get a lot of use out of these. These are the distributive rules for the arrow. And over here are the same ideas for if and only if. Again, this is the one I use the most in here. More often than not, I'm using this one. Questions? Back over here where it belongs. That's my left-hand side, the exclusive OR. It's true when one of them and only one of them is true. Now let's do this side. P or Q. That's the inclusive OR. P and Q is only true when both are true. The negation of P and Q and now I need this whole thing, which is really those two together. Yes? P or Q and not P and Q. So that's these two. And is true when both is true. It worked. If I had things involving exclusive OR in that table, I could make use of it to simplify things. This is disgusting. One of the problems with legacy code, and it's the same problem in hardware engineering with legacy equipment, is that you get wiring that looks like somebody threw a plate of spaghetti on the equipment and you don't know what goes where, right? And unless you strip it all out and reconfigure it manually, you're stuck. Unless you're going to rewrite this entire database of legacy code, don't touch it. It works. It's magic. Trust in the old magic. That's disgusting. Why is it like this? I don't know. People kept building and adding on. Fine, we'll deal with it. I claim this can be made simpler. So let's think about table 6, because this is all ands, ors, and nots. I don't have to use table 7 or 8. Let's just use table 6. I have all the way on the left a not outside a set of parentheses. I have a distributive rule. What does my distributive rule allow me to do here? Not as it's currently written. The double negation is only applied to a single item. But what I could do is I could distribute, right? Only there's a not and an and that's De Morgan. So when I distribute over an and, I got to use De Morgan's law. So this is equivalent to negate the first thing, flip the operation, negate the second thing, leave everything else alone. Now, I am remembering my geometry classes. And in my geometry class, every time I did something, I had to write down why I did it. So over here on the other side, I'm just going to write myself, hey, this was De Morgan. Statement, reason, statement, reason, statement, reason. They call them two-column proofs in high school geometry, and I hated them. But at least it gives me a way of keeping track of what I've done. But now, Roman, now I can say, okay, I've got not parentheses, not P. Here's my double negation. All right, let's keep going, see how much simpler we can make this. Looking at what you see in table 6, do any of those patterns match this pattern? I understand if you don't see this immediately. You've been looking at this list for all of about 3 minutes, and pattern matching takes time. But let's see if we can find something. My jump is that I see P or inside each of these parentheses. But I see something different here, right? So if I thought of this as P or thing and P or thing, that looks like the distributive rule. P or, and then I believe the parentheses has Q and R. This looks like the other side of that. So I can undistribute, I can factor out. It's really the distributive rule, but it's P or, not Q and Q. All right, I'm going to be meticulously detail-oriented. My brain sees not Q and Q. I'm sorry?
I thought the and was another not, and I was like, why did that go from Q to not Q?
Nope, that's an and. I just have sucky handwriting. Those should kind of the way go back. There's a thing with not Q, not P and P in the same thing, isn't there?
Negation law.
But here's where I have to be a pain in the ass. That one in the book is written P and not P. This one's written not P and P. I can switch the order commutative rule. And then by my negation law, what replaces that entire expression inside the parentheses? False. Now I go to the, what did they call them? Identities, absorption, something up at the top. The identity law, and that says when you are ORing with an F, you don't care about this part, you only care about this. All of that giant mess of logical expressions can be simplified to one propositional variable. Tell me whether P is true or P is false, nothing else in that matter. If I could simplify my code like this, my database would go from 20,000 lines to 3,000. I like that. In terms of physical circuitry, I could be looking at what was 7 or 8 different gates and therefore 3 different chips in the TI library. Each chip is a couple dollars. I just took this from 3 different chips, 15 bucks, to nothing. Is the lamp on or off? That's all I need to know. Now, some people will tell me that this is no shorter. And I understand that perspective because you need that list in front of you to do this until you've internalized and memorized that entire list. And that ain't never gonna happen, people. We don't use this that often. So I don't know. I still think truth tables are the easier way to go. But if you've got that in front of you, this is not a bad way of doing it. But very much like an algebra class, I've got to do all the factoring and distributing and reversing and double negatives and all of De Morgan. I need to do that stuff frequently enough to become familiar with it. Questions?
Would you put that in a word sentence? Like we did with the, if it snows, just
This
two
thing?
statements, yeah.
Yes, but I think I'm going to work right to left.
And that's fine. I just wanted to see it happen with words because it helps me.
It is snowing or it is freezing outside, and it is not snowing and freezing outside. That's disgusting. I don't know anybody that actually talks like that. And this is the downside of formal logic. It's an upside, though, to code thinking, because really your computer is an idiot and only thinks in trues and falses, ones and zeros, that's it. And if you told it to do it that way, that's your fault. So the computer's an idiot. We have to speak to the idiot. You all are smarter than that. That's my goal. More questions? One of the rules in that table on table 6 is the associative rule. If they're all ands or all ors, it doesn't matter where I do them first. Which means I don't have to restrict or to just 2. Or in 3 works in any way. Or in 4 works in any way. I could have as many ors as I want. So instead of writing thing 1 or thing 2 or thing 3 or thing however many, I'm going to write this like a loop. I'm going to write or. Start your counter at 1, go to n, proposition I. It's just a for loop. For 1 to n, do an or. And I can do it for ors, I can do it for ands, because when they're all the same, the order in which I do them by the associative property doesn't matter. That only works when they're all exactly the same. All have to be and, all have to be ors. De Morgan's law. De Morgan's law could apply to that whole set of parentheses, because that's really what this is. It's a giant set of parentheses. So I can now take De Morgan and write it not the giant or. Now, what did De Morgan say to do? De Morgan said you had to negate the individual piece. But also, flip what around?
And
So that has to become an and. I have to flip all the ors. And similarly, if I start with a bunch of ands, then when I negate the whole thing, I get a bunch of ors. Now, this one I like in words. If I say all of these with an or, right? Then any one of them can be true. Not A or B or C or D or E means they all have to be false. All have to go the other way. And if I want all of them, well, the opposite of that is saying, well, any one of them can be not. We talked about satisfiable, consistent system specifications. A proposition is satisfiable if at least one row ends in a true. So our system specifications are consistent if the proposition A, and if and only if B, if and only if C, if and only if D is not a contradiction. In other words, if there's at least one true in that last row of the truth table. And a Sudoku is a satisfiability problem. That is in the textbook as the last example. Page, example 9, I believe it's page 32. If you came in late and you still have homework for me, please bring it up. Otherwise, I will see you all Friday. Have a wonderful rest of your day.